In this lecture, we will see few examples which were past year gate questions that came with reactions as well as recycle and some design based questions with multiple reactor and distillation column. So this is one of the question. Now if you read the question, this is maybe gate 2007 question. If you read the question, it says that a simplified flow sheet is shown in the figure for production of ethanol from ethylene. The conversion of ethylene in the reactor is zero point 0.3. So the ethylene conversion is zero point 0.3, and the scrubber following the reactor completely separates ethylene as top product and ethanol and water as bottom. The last distillation column gives an ethanol water azeotrope 90 mole percent ethanol as a final product and waste as water. The recycle to purge ratio is 34. Now this is the reaction, and for an azeotrope product rate of 500 moles per hour, the recycled gas flow rate is this much. So to proceed with this question, let me draw a rough diagram of the process. This is the process going to the reactor. Now this is the scrubber, and this is the recycle shown in the question. This is the recycle shown in the question, and wash water is added. Here, water is added, and few fraction of the gas is purged. This is common line. This is purged, and after that, in this distillation column, azeotropic and wastewater. This is azeotropic, SVO, and waste water. Now, in the reactor, it is said the conversion is 30%. So here is conversion is 30%, and the scrubber separates ethylene product as pure ethylene. So this is pure. This is pure, and let the reaction be A plus B gives E. So A is ethylene, B is water, and E is ethanol. So for reaction A plus B gives ethanol, suppose A inlet in the reactor is FA in. I am denoting inlet of the reactor is FA in. Also, let me write some other data what are given. The recycle to purge ratio is 34. So, so let this stream be F recycle A, because A is getting completely recycled pure A. So this is recycled to A, and let this be FPA. This is purge pure A. So this stream is FPA. Let this stream be F azeotropic. Let this stream be F wastewater. Let the feed be FA naught and FB naught. So F and FA in is this part of the FA in. FA in and B is FB naught. There is no inlet 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 of reactor, and out initially inlet has no ethanol, and after reaction the conversion is said to be 0.3. So FA in 1 minus 0.3, and B will have FB naught minus FA in 0.3, and the E will become FA in into 0.3. So at outlet, these are outlet of reactor. At outlet, this is A, this is B, and this is E. These are the moles at the outlet of the reactor. So if we do A balance at the outlet of the reactor, Let me do A balance. A balance in the sense ethylene balance. Ethylene balance. If we do ethylene balance, then if A in 1 minus zero point 0.3, which is the outlet of the reactor. This is outlet, outlet of the reactor. This will be equals to the recycle A, which is going plus purge, which is going out of the system. Now the ratio of recycle to purge is 30, sorry 34. So F R A by F purge A is equals to 34. So in this expression we can easily write that 1 plus If let me substitute FPA is 1 by 31 by 34 FRA. So 1 by 34 FRA. Also, this is ethanol, which is separated from here. Ethanol, ethanol, ethanol is separated from here. So if we do ethanol balance, E balance, balance, ethanol, ethanol balance, ethanol balance, then we will have expression FA in 0.3. This is the outlet of the reactor, outlet ethanol of the reactor, which we get from here. This is the outlet of A, which we get from here. If A in 0.3 is equals to, now the azeotropic has 90 mole percent of ethanol. Azeotropic has 90 mole percent ethanol. So if the product flow is FAZ, then 0.9%, 0.9 fraction will be ethanol, azeotropic. So we can simplify this as if A in is equals to 3FAZ. Now this relation says that whatever be the product rate, the inlet of A or ethylene inside the reactor is 3 times of product formed. So from this data, we get a relation between 0.7 if A in is 3 times FAZ into 3 FAZ is equals to 34, 35 FRA. This is FRA. Now, in the question we have been asked the recycle flow rate. Recycle flow rate. So FRA, which is the recycle flow rate, which is our target of the problem. If RA is equals to 0.73 into 34 by 35 into FAZ. FAZ is that is azeotropic product rate is 500 moles per hour. 500 moles per hour. This will be equals to this will be equal to 1020 mole per hour. If you do calculation in calculator, this will be 1020 moles per hour. So the answer is this option C. Now second part, the second part says that for the same process, if fresh feed H2 fed in the reactor, the FBO is given as 600 moles per hour, and wash water for scrubbing is 20% of condensables coming out of the reactor. The condensables are ethanol and water. Ethanol and water. Water. These are the condensables from the reactor, and it is 20%. So we can write that the water remaining, if you do water balance, our question is But our question is to find the water flow rate at the bottom of the distillation column. So we have to do water balance. Now to water balance, the water coming out of the reactor is this. This is the water coming out of the reactor, which is F B naught minus Fa in multiplied by 0.3. This is the water coming out of the reactor plus 20% of the condensables. Now the condensables are water and ethanol. So this term plus this term is the total condensable coming out. The total condensables coming out is Fb naught minus Fa in to 0.3. This is the plus water plus ethanol is this one Fa in Fa in into 0.3. This is ethanol outlet, water outlet, ethanol outlet. This is water outlet. This is equals to the water going to the azeotropic product, which is said to be 0.1% of azeotropic flow rate plus the remaining wastewater, let denote by W. Now, if we simplify this expression, this term and this term get cancelled, and zero point 0.2 Fb naught plus Fb naught is equals to 1.2 Fb naught minus Fa in into zero point 0.3, which is equals to zero point 0.1 FAZ plus F wastewater. Now, if wastewater is equals to 1.2 Fb naught minus zero point 0.3 into F, this value is equals to this one. So zero point 0.3 into FAN is equals to 0.9 FAZ. So I will write 0.9 FAZ minus zero point 0.1 FAZ, which is equals to 1.2 into FB naught is FB naught, the water supplied to the reactor is 600 minus FAZ, the product flow rate in the question is 500 moles per hour, which will be equals to 1.2. If you do the calculation, it will get 220 moles per hour. Mole per hour. The answer is 220 mole per hour. Now, let us go to the second question. Now, second question is from GATE 2015. Now, it states that this schematic diagram is present in the shown in the process below. Now, this schematic diagram steady state process shown in the below. The figure, the fresh feed to the reactor consists of 96 mole percent A and 4 mole percent inert. The stoichiometry of the reaction is A to C. A becomes C. A part of the reactor effluent is recycled. The molar flow rate of the recycled 0.3 F. It is already shown. The product stream contains 50 mole percent C, and the percentage conversion of A in the reactor based on A entering the reactor at point 1 in the figure. So from the question we can understand that we have to find the percentage conversion of A in the reactor based on A entering the reactor at point, means the actual conversion of the reactor or single pass react conversion. Now, as this reaction is A to C, remember, if if any reaction is mole conserving, that left side or right side has same number of moles of the reactants and products, then in overall system the total molar inflow of the system will be equal to the total molar outflow of the system. So in this system there is only one molar inflow, which is F, and outflow is P. So we will easily can write one equation without hesitating. F is equals to P. So the molar inflow of the molar F inflow value variable F will be equals to the product flow rate P. Okay, now the reaction. Now it says uh, the product stream P contains 50 mole percent C. Okay, Suppose at point 1 the inlet of the reactor be at point 1. Suppose we write the reaction as A to C. Now let inlet be FA in, that is the stream flow here, FA in, FC in. Here it is given 50% C, 50% C. Okay. Now from the reaction FA in, the inside inlet of the reactor, inlet reactor, it will have FC in, because there will be some part C which is recycled in the reactor, and also in the product nothing, product P. Okay, this is pure separator. The product P will also have 50% C. The product P will also have 50% C. Now this is the inlet of the reactor. Outlet of the reactor will be, conversion is unknown, so let it be FA in 1 minus X. So and the product C will be FC in plus FA in into X conversion, which is added. Now the recycle is 0.3 F. So total molar outflow, as this reaction is A to C, so the molar, uh, there is no change in density. As you know that molar F is equal to F naught 1 plus epsilon A into conversion A. Here epsilon A is a change in stoichiometry, which is 0. So inlet moles will be equals to the outlet moles. So the inlet moles will be F plus zero point 0.3, which is 1.3 F, and outlet will be also same. So we have one data given that if C inlet plus if A inlet into X, which is C, mole of C, mole C by total mole, which is equals to 1.3 F, is given by zero point 0.5. This is given in question. So if we simplify this, if A in X plus if C in is equal to 1.3 into zero point 0.5, zero point 0.5 into F. Now FC in, the inlet C, the inlet C is of 50% concentration. So FC in, FC inlet is equals to 0.5, it is 50% concentration into zero point 0.3 F. This is the C inlet. There is no external or extra C which is added in the system. Only A is fed to the system. So this is equals to 0.15 F. Now also if A in, if A in, if A inlet of the reactor will have, if A in, yeah, the fresh feed consists of, okay, the if A in, the fresh feed has 96 mole percent reactant F, 0.96, 0.96 F, and the recycle part of the reactor effluent is recycled. So recycle part 50% is total C, and inert is 4 mole percent. Now if you do mole balance of the inert, 0. Okay, I cannot write it here. If you do mole balance of the inert, if 4% is present at the inlet, the outlet will also be have 4%, because 0.4 F is equals to Y inert into product. Now F is equals to P from this relation. So Y inert is equals to 0.4. So inert will be 0.4, sorry, 4 mole percent, 0.04, 0.04, 0.04 and this is also 0.04, so 4 mole percent. Now 50% is C, 4% is inert in the product, so remaining will must be A. So A is 46%. So if we put the value, the remaining 46%, 0.46 into 0.3, this is the recycle. So if we simplify this, we get 1.098F. Now put FA in value 1.098 F into X plus FC in is 0.15F is equals to 1.3 into 0.5 F. The entire F get cancelled. We have a simple expression relating X and remaining numerical constant. 1.3 into 1.3 into point 1.3 into point 0.5, 3 into point 0.5, which is equals to X. X is equals to, this is equals to 13 5 is 65, so this is equals to 0.65. So this is equals to, if we calculate this value, we get 0.45537. Conversion is 45.537. So the answer is not there. This answer should not be in percentage, it should be in fraction. So the answer should be written as this one, not this one in GATE exam. This one is wrong. This one should be written because it is asking in fraction only, not in percentage. Let us go to another question, which is GATE 2024 question. Now it reads that consider the process in the figure for manufacturing B. The feed process is 90 mole percent of A. Here it's 90% A, and a close boiling inert component I. At a particular steady state, the B product rate is 100 kilomole per hour. Single pass conversion is 0.5. Recycle to purge flow is 10. So recycle to purge flow is 10. So let me draw this diagram. Can I draw here? Yeah, I can draw here. So I will use notation that this is recycle flow rate. This is purge flow rate. Suppose, and these are the concentration. Product flow rate FB is equals to 100 kilomole per hour. Okay. Now this is also, it is given that recycle to purge is 10. So it means R is equals to 10P. This equation we will use. Also, the feed is 90 mole percent is already given. Single pass conversion is 50%. So here conversion is 50%. This is 50%. And uh, this is a separator, and pure B is separated. Remaining is recycled. So it will have A and inert. So let the mole fraction of A here be XAR. AR represents inert. Sorry, AR represent recycle, and there will be inert. So at first, whenever there is inert, we will do the inert balance. So inert does not participate in reaction. Inert balance. Whenever there is inert in this system, do the inert balance. This will give a meaningful expression. So of 10% of feed. Suppose if 10% of feed, F is feed. Suppose this string is feed. 10% of feed is, and it is going from the purge only, is equals to some 0.1 F is equal to some concentration, which is 1 minus XAR, because A species A and inert are only present. So inert concentration is XAR into purge. So this is one relation. What they have asked the flow rate of A in the purge stream in kilomole per hour rounded off to decimal places. Okay, so they have asked is the flow rate of purge stream, which is flow rate of A in the purge stream, which is equals to XAR into P. This value they have asked. Now inert balance from this, we may need this equation, let it be. Now from the reaction, it is shown that 50% conversion is happening. So inlet of the reactor is FA inlet, there is no B. Outlet FA in minus 2 zeta and B will be zeta. Conversion of A is this minus this quantity minus this quantity divided by this quantity of 2 zeta by FA in. So zeta is equals to FA in conversion of A by 2. The conversion is already given zero point 0.5 or 1 by 2. So 1 by 2 FA in divided by 4. Now if B out is given by zeta, which is already taken by 100 kilomole per hour. So zeta is FB, which is 100 kilometer per hour, which is given and which is again equal to FA inlet by 4. So FA inlet is 4 times FB. So here 100, so FA inlet inside the reactor will be 400. Now, now outlet is completely recycled. So outlet, so if A out is equals to F A in minus 2 zeta. F A in is 4 times B naught, 4 B naught, sorry, 4 B minus 2 zeta is already B, 2, 2 F B is equals to 2 F B. Now F out is XAR concentration XAR into R plus T equals to XAR into R plus T. Now R is 10P, it is already given. So 11 XAR into P is equal to 2FB. Now XAR into P, which is our question. So 2 into FB is 100 divided by 11. So this value is 200 by 11 and this is equal to 200 by 11, which is equals to 18.18.1818. So this is the answer. This much kilomole per hour is leaving the kilomole per hour of A is leaving through purge. Now let us move to another question, which is of GATE 2022. Now it says that consider the process flow sheet in the figure. An irreversible liquid phase reaction A to B is having A to B mole is conserving. So this is the reaction occurs at 1 meter cube CSTR, where X is the mole fraction of A. A small amount of inert I is added to the reactor. The reactor effluent is separated in a perfect splitter, recover pure B product the down the bottom and the B free distillate. This is B free distillate. A fraction of distillate is purged and rest is recycled back to the reactor. Particular steady state, the recycle rate is 200 and product rate is 100. Purge rate is 10. With this information, it is needed to find inert feed rate into the process. So inert feed flow rate. So let inert feed flow rate be F I naught. This fresh feed be F A naught. This suppose this as be RA. So suppose this is the bottom product FB, which is already this value is already given. This is purge. Now this is purge by system. So directly I will write the inert balance. FIO is equals to concentration of inert at the purge Xi at P. Let the concentration here be Xi. Here is the concentration Xi. Okay. Now this is a mole conserving system. So Fa naught plus Fa I naught is equals to 10 plus 100. So Fa naught plus Fi naught is equals to 10 plus 100, which is 110 kilomole per hour. This might be handy. Now, as this is CSCR, so Fa in plus RAV is equals to Fa. Suppose these streams are Fa, Fb, concentration will be Xa, and the remaining will have remaining will be E naught and B. So let let it be xi prime and xb prime, xb. Let me denote this as x prime to maintain the uniformity. Let this be xi prime and this be xi. At these at the reactor outlet it is xi, and at the distillate of the perfect cylinder all are primed variables. Similarly, RBV, there is no inlet in the B, 0 plus is equals to FB. FB is already given 100 kilomole per hour. Now RA is equals to minus RB. This is from the stoichiometry of the reaction. So RB is equals to K into XA. So from this expression, RB is equals to K XA, V is equals to 100 kilomole per hour. Now the concentration of XA will be 100 divided by K. K value is 164 kilomole per meter cube per hour. So in meter per meter cube into 1 meter cube is 164, and this value is equal to 0.60975. So this is the concentration. Now this is the concentration of A. Now also see one thing. This is recycled 200. This purge is 10. This is 100. So 200 plus 10 plus 100. This must be the flow rate of this stream. 200 plus 100 plus 10 is equals to 310. So inlet must be 310 kilomole per hour to the splitter. 10, 200 plus 100, 310. And as this is a mole conserving reaction, so the reactor inlet will also have 310 kilomole per hour. So 310 kilomole per hour from concentration of A, we can easily find the outlet flow rate of A, which is equal to XA into 310 is equal to 100 by 164 into 310, which we will get as 189.0243 kilomole per hour. This is the molar flow rate of A outlet of the reactor. Now this is perfectly recycled. So the distillate will have 189.0243 A flow rate. Suppose this is Fa prime, A flow rate, and the concentration A, Xa, prime are concentration or variable. So Xa prime will be 189.0243 divided by this. This is 200 plus 10, 210. This value will be equals to, this value is equals to, it is already done here. This value is equals to 0.90011, 0.90011. So, and here only A and E naught are recycled. So Xi prime would be 1 minus Xa prime, which is equals to plus 1, which is equals to 0.9987. So we get Xi prime. And I mentioned this as I prime. The distillate concentration. This is the concentration and this is separator. So Xi prime will be here in purge also. So this is xi prime. Xi prime is given by 0.9987 into per flow resistance. So 9.987. Sorry, my mistake. This is 0.09. 0.09. Oh, wait. 0.09. So this is 0.09987 into 10, which is equal to 0.998 kilomole per hour. So this is the flow rate entering the system. Flow rate of inert entering the system 0.998 kilomole per hour.